PostgreSQL did not appear overnight. It began as a research project. The year was 1986. The place was the University of California, Berkeley. A brilliant computer scientist named Michael Stonebraker led the effort. He had already created a successful database called Angra. Now, he wanted to build something even better. He saw the limitations of existing database systems. They were just not well suited for the complex data types that were emerging. He envisioned a system that could handle more than just simple numbers and text. This new project was named Postgres, signifying its role as a successor to Ingres. The core goal was clear. The team wanted to create a database that could understand objects. This was a revolutionary concept at the time. Traditional databases stored data in simple, flat tables. Postgres aimed to support complex data structures directly. It would allow users to define their own data types. It would also let them define functions to operate on that data. This would make the database more powerful and flexible. It was a bold step forward. The project was designed to solve the data management problems of the next decade. The team at Berkeley was building for the future. The initial funding came from several government agencies. The Defense Advanced Research Projects Agency, or DARPA, was a key supporter. So were the Army Research Office and the National Science Foundation. Their support was crucial. It allowed the Berkeley team to explore these new ideas without commercial pressure. The focus was purely on research and innovation. They were free to experiment with new architectures and features. This academic freedom was essential to the project's early development. It laid the foundation for the robust system that we know today. The team published many papers, sharing their findings with the world. Over the next several years, the PostgreSQL team worked tirelessly. They developed the initial concepts into a working prototype. The first version demonstrated the power of its object relational model. It introduced features like rules, procedures, and extensible types. These were groundbreaking ideas. They showed that a database could be more than just a passive repository for data. It could be an active part of an application's logic. The work done in these early years at Berkeley was fundamental. It established the principles that still guide PostgreSQL's development. The seed planted in 1986 was beginning to sprout. The first versions of Postgres used a query language called Quell. This was the same language used by its predecessor, Angre. Quell was powerful and elegant in its own way. It was well liked within the academic community. Many of the original developers were very familiar with it. For them, it was the natural choice. The language had a syntax that was different from what most people use today. It was based on tuple calculus, which is a formal language for database queries. The team believed it was a superior way to interact with their advanced database system. It fit well with the project's research-oriented goals. However, the world outside of Berkeley was changing. A different query language was gaining incredible momentum. This language was SQL, which stands for Structured Query Language. SQL was developed by IBM in the 1970s. By the late 1980s, it was becoming an industry standard. The American National Standards Institute and the International Organization for Standardization had both adopted it. Commercial database vendors were all rallying around SQL. This created a powerful network effect. More developers were learning SQL, more tools were being built to support it. The industry was choosing its language. The Postgres team faced a critical decision. Should they stick with the technically familiar Quell, or should they embrace the industry standard SQL? Sticking with Quell would make it harder for new users to adopt Postgres. They would have to learn a new language. This would be a significant barrier. Adopting SQL would make Postgres instantly more accessible to a much wider audience. It would allow the project to move beyond the confines of academia. It was a practical choice that would determine the project's future. The debate was significant, but the path forward became increasingly clear. In 1994, two of Stonebraker's graduate students, Andrew Yu and Jolly Chen, made a bold move. They replaced the Quell query interpreter with one that used SQL. This was a massive undertaking. They didn't just add SQL support, they fundamentally changed the core of the system. This new version was initially called Postgre 95. The change was a turning point. It signaled a shift from a pure research project to something that could be used in the real world. By adopting the standard language of data, Postgres 95 opened the door to a global community of developers and users. This decision was one of the most important in its history. The release of Postgres 95 was a major milestone. It brought the project into the modern era with its SQL capabilities. However, the name itself soon felt dated. The 95 was tied to the year of its release. A more timeless name was needed. In 1996, the project was renamed PostgreSQL. This new name was chosen carefully. It honored the project's origins as Postgres. It also clearly indicated its new support for SQL. The name change marked another important transition. It was the moment the project truly became a community effort independent of its Berkeley roots. It was ready to stand on its own. A crucial decision was made along with the name change. PostgreSQL would be released under a liberal open-source license. This license, now known as the PostgreSQL license, is similar to the BSD and MIT licenses. It allows anyone to use, modify, and distribute the software for any purpose. There are no fees, there are no restrictive terms. This was incredibly important. It ensured that PostgreSQL would remain free and open forever. It prevented any single company from controlling its destiny. The source code was now available for everyone to see, to learn from, and to improve. This open source model was the key to its future success. It invited collaboration from all over the world. Developers were no longer limited to a small team at a university. Anyone with the right skills and a good idea could contribute. This created a dynamic and decentralized development process. Patches and new features could come from anywhere. A programmer in Japan could fix a bug found by a user in Brazil. A developer in Europe could add a feature requested by a company in the United States. The project became a global collaboration. The move to open source also fostered a culture of quality and transparency. With many eyes on the code, bugs were found and fixed quickly. Discussions about new features happened in public mailing lists. Decisions were made based on technical merit and community consensus. This open process built a tremendous amount of trust. Users knew that the software was being developed by a dedicated community focused on creating the best possible database. This trust was essential for businesses to consider using PostgreSQL for their critical applications. It was the start of a new chapter for the database. With PostgreSQL now open source, it needed a structure to guide its development. The project could not rely on the university anymore. A new form of leadership was required. This led to the formation of the PostgreSQL Global Development Group. This group is often simply called the core team. It is not a company. It is a committee of dedicated long-term contributors. They are responsible for managing the project. They coordinate releases, guide the overall direction, and act as final arbiters in technical debates. Their role is one of stewardship, not ownership. The community itself is much larger than the core team. It is made up of thousands of people around the world. There are the contributors who write code, fix bugs, and improve the documentation. There are advocates who promote PostgreSQL at conferences and in articles. There are users who test new versions, report issues, and help others on mailing lists and forums. This diverse community is the lifeblood of the project. It is a meritocracy. Your influence is based on the quality of your contributions, not your job title or where you work. This flat structure encourages participation and innovation from everyone. The main channels for communication are public mailing lists. This is where most of the work happens. There are lists for developers, for users, and for specific topics like performance tuning. Every proposed change to the code is submitted as a patch to the developer mailing list. It is then reviewed publicly by other members of the community. This peer review process is rigorous. It ensures that all new code is high quality, well-tested, and secure. This open and transparent process is one of PostgreSQL's greatest strengths. It builds confidence and leads to a more stable and reliable product for everyone. Over time, this community model has proven to be incredibly resilient and effective. It has allowed PostgreSQL to grow and evolve for decades. Commercial companies have also become a vital part of this ecosystem. Many businesses now employ developers to work full-time on PostgreSQL. They contribute code that benefits the entire community. They also offer commercial support training and specialized versions of the database. This creates a healthy symbiosis. The open source project provides a powerful, free database. The companies provide the services that many enterprises need. This partnership has been essential for PostgreSQL's widespread adoption. PostgreSQL has always been, a pioneer of advanced database features. Its development history is really a story of continuous innovation. One of its earliest and most important features was multi-version concurrency control, or MVCC. This was actually implemented long before many commercial databases had it. MVCC allows readers and writers of the database to not block each other. When you are reading data, you see a consistent snapshot of the database. You are not affected by other transactions that are changing the data at the same time. This results in much better performance for systems with many concurrent users. It is a cornerstone of PostgreSQL's reliability. Another key area of innovation is extensibility. From its very beginning as Postgres, the system was designed to be extended. Users can define their own data types, functions, operators, and index methods. This is incredibly powerful. It means you can teach the database to understand new kinds of data. For example, the PostGIS extension turns PostgreSQL into a world-class geospatial database. It adds support for geographic objects and queries. This extensibility is not just an add-on. It is built into the core architecture. It has allowed PostgreSQL to adapt to new challenges and use cases over the years, keeping it relevant and powerful. PostgreSQL is also known for its strong adherence to the SQL standard. While other databases often implement their own proprietary versions of SQL, PostgreSQL strives for compliance. This makes applications more portable. Code you write for PostgreSQL is more likely to work with other standards-compliant databases. At the same time, it has introduced many advanced SQL features. It was an early adopter of window functions, common table expressions, CTEs, and recursive queries. These features allow developers to write complex queries in a more elegant and efficient way. This commitment to both standards and advanced features makes it a favorite among developers. The reliability and data integrity of PostgreSQL are legendary. It has a strong reputation for protecting user data. Features like point-in-time recovery, or PITR, allow administrators to restore a database to any single moment in time. This is invaluable for disaster recovery. The write-ahead logging (WAL) system ensures that no committed data is ever lost, even in the event of a server crash. These features are not optional extras. They are fundamental parts of the database. This focus on robustness has earned PostgreSQL the trust of organizations that cannot afford to lose data. It is a database built for the long haul. The journey from an academic project to an enterprise-ready database was gradual. In the early 2000s, PostgreSQL was mostly used by universities, startups, and tech enthusiasts. It was seen as a powerful but niche alternative. Many large companies were hesitant to use open-source software for their critical systems. They were more comfortable with commercial vendors who offered support contracts. They worried about who they would call if something went wrong. The PostgreSQL community had to prove that its model could provide the reliability and support that large businesses needed. The quality of the software began to speak for itself. Slowly but surely, perceptions began to change. Companies started to notice the technical superiority of PostgreSQL. They were attracted by its advanced features, performance, and rock-solid stability. The lack of licensing fees was also a major factor. As data volumes grew, the cost of commercial database licenses became a significant expense. PostgreSQL offered a way to escape this vendor lock-in. Early adopters were often technology companies and internet startups. They had the technical expertise to manage the database themselves. They saw the value in its open nature and vibrant community. These companies became important advocates for PostgreSQL. By the 2010s, PostgreSQL had reached a tipping point. It was no longer just for startups. Major corporations began adopting it for mission-critical applications. Financial institutions, telecommunications companies, and large retailers started migrating from expensive proprietary databases. They found that PostgreSQL was not only cheaper, but often more reliable and performant. A strong ecosystem of companies offering commercial support had also emerged. This gave large enterprises the safety net they required. They could get 24/7 support from companies like Enterprise DB, 2ND Quadrant, and Crunchy Data. This removed one of the final barriers to adoption. Today, PostgreSQL is a trusted choice for businesses of all sizes, from the smallest startups to the largest multinational corporations. Its reputation for reliability, security, and performance is second to none. The list of companies that rely on PostgreSQL is long and impressive. It includes names from every industry sector. This widespread adoption has created a virtuous cycle. As more companies use PostgreSQL, more of them invest in its development. This leads to an even better database, which in turn attracts more users. This powerful feedback loop has cemented PostgreSQL's place as a top-tier database system. To understand the impact of PostgreSQL, let's look at some real-world examples. Apple is one of the world's largest companies. It uses PostgreSQL for a wide range of critical internal systems. For many years, parts of Apple's iCloud and iMessage infrastructure relied on it to manage vast amounts of user data. The database's ability to handle high transaction volumes and ensure data integrity was essential for these services. Apple values the stability and robust feature set of PostgreSQL. Their use of the database demonstrates its capability to operate at an immense scale, supporting hundreds of millions of users around the globe. Instagram, the popular photo and video sharing service, is another famous example. When Instagram was first launched, it ran entirely on PostgreSQL. The database stored all user data, photos, and relationships. As the service grew explosively, its database had to scale with it. The Instagram engineering team famously pushed PostgreSQL to its limits. They sharded the database, which means they split the data across many different servers to handle the load. Their success showed the world that PostgreSQL could power a fast-growing web-scale application. While they have since moved to other technologies for their primary data store, their story remains a testament to PostgreSQL's power. Spotify, the leading music streaming service, also relies heavily on PostgreSQL. It is used for many back-end systems, including those that manage metadata about songs, artists, and albums. It also plays a role in running their internal business logic and administrative systems. For Spotify, the reliability and flexibility of PostgreSQL are key. They need a database that just works, allowing their engineers to focus on building new features for their users. The ability to use JSON-B, a powerful feature for storing semi-structured data, is also a significant advantage. This allows for greater flexibility in how they model their data. These examples show the versatility of PostgreSQL. It is not just for one type of application. It can be the transactional backbone for a massive company like Apple. It can power a rapidly scaling social media platform like Instagram. It can be the reliable data store for a content delivery service like Spotify. In all these cases, companies chose PostgreSQL because of its technical strengths. They needed reliability, performance, and advanced features. They also benefited from the open source model, which gave them freedom and control over their technology stack. These stories have inspired countless other companies to trust PostgreSQL with their own data. In the modern technology landscape, the cloud is dominant. Today, in 2025, most new applications are built and deployed in the cloud. PostgreSQL has adapted perfectly to this new era. All major cloud providers, including Amazon Web Services, Google Cloud, and Microsoft Azure, offer PostgreSQL as a managed service. These services, like Amazon RDS for PostgreSQL and Azure Database for PostgreSQL, make it incredibly easy to set up, operate, and scale a PostgreSQL database. They handle tedious administrative tasks like backups, patching, and replication. This allows developers to focus on their applications instead of managing database infrastructure. The availability of managed PostgreSQL in the cloud has massively accelerated its adoption. It has become the default choice for many developers building new cloud-native applications. They get all the power and features of PostgreSQL without the operational overhead. This has been a game changer. It has leveled the playing field, giving small startups access to the same powerful database technology as large enterprises. The cloud has made PostgreSQL more accessible than ever before. It is now just a few clicks away for any developer in the world. This has further solidified its position as a leading open-source database. In the enterprise world, PostgreSQL continues to challenge the dominance of proprietary databases. Many large organizations are actively migrating their systems from commercial databases like Oracle to PostgreSQL. This trend is driven by several factors. Cost is a major one. PostgreSQL's open-source license eliminates expensive licensing and renewal fees. But it's not just about cost. Many enterprises now see PostgreSQL as technically superior. They are drawn to its open architecture, active community, and rapid pace of innovation. The ecosystem of support and tooling around PostgreSQL is now mature enough to meet the stringent requirements of any large business. The combination of a strong open-source community and a robust commercial ecosystem gives enterprises the best of both worlds. They get a world-class, free database developed by a global community. They also have the option to purchase enterprise-grade support, training, and specialized tools from a variety of vendors. This competitive market for services ensures high quality and fair pricing. This model has proven to be a winning formula. It has allowed PostgreSQL to thrive in the demanding enterprise environment, earning the trust of the world's most conservative and risk-averse organizations. PostgreSQL is no longer an alternative. It is a mainstream top-tier choice. As we stand here in mid-2025, the future of PostgreSQL looks brighter than ever. The development community continues its yearly release cycle, consistently delivering significant improvements. The recent releases have focused on enhancing performance, scalability, and ease of use. We are seeing major advancements in logical replication, which allows for more flexible distribution of data. There is also ongoing work to improve parallelism for complex queries, allowing PostgreSQL to take full advantage of modern multi-core processors. These incremental but powerful enhancements ensure that PostgreSQL stays at the cutting edge of database technology. Looking toward the near future, several key trends will shape PostgreSQL's development. One major area is making massive databases even easier to manage. As data volumes continue to explode, features that improve partitioning and sharding will be critical. The community is actively working on built-in sharding capabilities, which would make it simpler to scale a database horizontally across many servers. Another focus is on analytics. Enhancements to the query planner and the addition of new features will continue to make PostgreSQL a stronger platform for both transactional and analytical workloads, blurring the lines between these traditional categories. The rise of artificial intelligence and machine learning also presents new opportunities. We can expect to see tighter integration between PostgreSQL and AI or machine learning frameworks. This could involve features that allow for machine learning models to be run directly inside the database. This would reduce data movement and allow for real-time predictions based on the latest data. Extensions like PG_vector are already making PostgreSQL a powerful database for vector similarity search, a key component of many AI applications. This trend of bringing computation closer to the data will likely continue, making the database an even more active and intelligent component of modern applications. Ultimately, the future of PostgreSQL will be determined by its community. This is its greatest strength. The global, diverse, and dedicated group of developers and users ensures that the project will continue to evolve to meet new challenges. Its open-source, collaborative model has been successful for nearly 3 decades. There is no reason to believe this will change. As long as there are interesting data problems to solve, the PostgreSQL community will be there to solve them. Its journey from a Berkeley research project to a global open-source powerhouse is a remarkable story, and the best chapters may still be yet to come.